Okay, so in this video, I'd like to go through direct assembly of the reactions for our frame example. So in the previous lecture, we formed and solved the joint equilibrium equations Ku equals p hat minus p0, and we solved for displacements by gas elimination, right? So p hat minus p0. Okay, so now we want to recover the external reactions. Okay, so just like the unknown joint displacements in the vector u, we can number the unknown external reactions 1 through the number of reactions. And for this frame, there's 5 reactions. There's 3 at the fixed support on the left, and then 2 reactions at the pin support on the right. Okay, so we'll use this numbering throughout our recovery of the reactions. Okay, so just like forming the stiffness matrix and load vectors, all right, each reaction is obtained by direct assembly from element contributions over dki plus 1 compatibility states. And we can represent that as a summation as shown here. So the ith reaction is the sum of dki plus 1 contributions to the ith reaction summed over j. All right. And for this example, there were 7 compatibility states. Okay, and the plus 1 is for compatibility state 0, which is due to the member loads shown here. For compatibility state 0, we impose 0 displacements to all the unknown joint displacements. So we just completely fix the structure again, like we did in the assembly of the equilibrium equations, and then we look at the effects of member loads on the compatibility state. Okay, so to this end, we look at the case of a uniform load on a fixed beam, which is what's happening here with the girder. All right, so this is WL over 2, WL over 2, and then WL squared over 12, and WL squared over 12. And then we want to write in the contributions to the reactions from this compatibility state. So this would be R1, 0, this would be R2, 0, and R3, 0. So the superscript is the compatibility state, and the subscript is the reaction number. And then this would be R4, 0, and R5, 0. Okay, so then we just match up, the contributions of the fixed end forces and moments occurring at and in the direction of each unknown reaction. So for this particular case, all the fixed end forces are occurring at other locations. All right, so this is happening up here, this moment's happening up here, as are these two forces and moments here. So none of those coincide with the R1 through R5 superscript 0. Therefore, all the contributions for this compatibility state are 0, because there's no member loads applied to members that are connected to the supports. Okay, this is not a general result, but that's just for this example. Next, we move on to compatibility state 1. This is where we impose U1 equals its numerical value that we obtained in the previous lecture, right? And we look at the contributions to the reactions for this compatibility state. Okay, so we do the same thing that we did before. We impose a unit value of the unknown joint, or what's now a known joint displacement, but I'll still impose it as a unit value. This joint does not move. This joint over here, also at the support, does not rotate. Okay, and that's a 1. But what we're going to do is take all the results within this compatibility state and multiply everything by the numerical value for U1, which is 0.061796 feet, right? Okay, and we draw the deflected shape of the structure, right? The beam goes into compression, the column on the right does not deform. And then we're going to label the reactions that we want to assemble. Okay, and next we want to use the fixed end forces shown over here on the right to determine what the contributions to the reactions are. Okay, So for the column on the left, right, it's going to look a lot like this case here. Turn it 90 degrees, right, and it looks like the column on the left. Okay, so now we're only concerned with what's happening down at the location of the reactions. So I'm just going to only draw what we need. Okay, so this will be a 12 EI over L cubed for the column, and this will be a 6 EI over L squared for the column. And then there's nothing happening over here, right? So those are zeros, okay? And there's no vertical contribution at the left end either, so this will also be 0, okay? But then to find the contributions to the reactions up here, 1, 2, 3, 4, 5, right? R1, 1, right, is going to be 12 EI over L cubed times 0.061796, right? And the sign on that will end up being negative because these two arrows are going in opposite directions, and this is a positive displacement, right? So 12 EI over L cubed, or negative 12 EI over L cubed, if you will, times 0.016796 should give you negative 18.792 kips, all right? And then R3 is going to be positive 6 EI over L squared times 0.016796, and that'll give you this contribution right here. Okay, and the other three contributions for 2, 4, and 5 are all zeros. Okay, so we'll keep this vector, right, because we're going to use it to sum things up at the end. Okay, so for compatibility state 2, we're going to move this joint up a unit amount to here, draw the deflected shape of the structure, something like this. This joint doesn't move, this joint down here doesn't rotate, okay? And then whatever we do within this compatibility state, we're going to multiply by the numerical value of U2. Okay, so we treat it as a positive 1 and then just take the numerical value. Right, in this case, it's a negative, very small number, right, times 10 to the minus 5 radian, or not radians, feet. Right? So the joint's actually moving down. All right, I drew it as up, but we want to think like computers, just keep consistent signs and then let the algebra work things out. Okay, and now you can just fast forward through me labeling these. Okay, so now we have the 5 contributions to the reactions for this compatibility state. And now we can draw the fixed end forces occurring at these locations are 1, 2, 3, 4, 5. Okay, so the only non-zero contribution is going to be due to the extension, axial extension of the column, which is EA over L. And that's going to affect R2, all right, for compatibility state 2. So 1, 2, 3, 4, 5. Okay, so this is going to be negative EA over L because R2 and EA over L are moving in opposite directions, or have arrows pointing in opposite directions, right? EA over L is down, R2 is up, all right? But then we have a negative algebraic value for the displacement. So negative EA over L times negative 2.2672 10 to the minus 5th gives us a positive 0.82186. Okay, so again, we just let the algebra work itself out. Right? Just still move everything as positive, and then the algebraic signs take care of everything. Okay, so that's the only non-zero contribution for this compatibility state. Okay, next is compatibility state 3, which is a rotation. So we'll rotate this joint a unit amount, right? And then everything we do therein is going to be multiplied by negative 0.001221 radians. Okay, and that's what we got from the numerical solution for the joint displacements. And now we can label the contributions. Okay, and next we can look at the fixed end forces and moments occurring at the support locations. Okay, so looking at this case here, right, that'll apply for both the girder and the column, turn it 90 degrees, right? But we get, just looking at the locations where we have contributions to the reactions, 2EI over L and 6EI over L squared. Okay, so really we're looking at this end for the column. All right, and there's some stuff going on in the girder, of course, but none of that's going to assemble into the reactions. So we have, 1, 2, 3, 4, 5 reactions. Okay, and we're going to take for R1, right, we're going to have a negative 6EI over L squared because that's moving or has an arrow in the opposite direction of R1. And then multiply that by negative displacement, negative 0.001226 rotation. And then that gives us this positive contribution to R1. All right, R2, 0. R3 is going to be 2EI over L, arrows rotating in the same direction, times negative 0.12261. And that gives us that negative 32.923. So we'll keep this vector and sum it up at the end. All right, so the next 4 compatibility states, I'll just go through on mute and they'll be sped up. It's very repetitive type work. Okay, so now that we've gone through all 8 compatibility states, right, DKI plus 1, all right, this is for CS0 up to 7, all right. If we sum up all those vector contributions that we assembled, right, we would get this total reactions for our system, all right, and we can draw those on the picture here, right? So we have negative 10.561, just means it's going in the opposite direction of what we assumed was positive. That's Kips. And then for 2, right, this is 1, 2, 3, 4, 5, positive 0.82186 Kips. And then the moment reaction is positive 79.828 Kip feet, all right? And then negative 4.439, which just means pointing to the left in the opposite direction of what we assume was positive, and then positive 14.178 Kips. Okay, so these reactions should satisfy equilibrium, right? And we can check that just like we do in statics, right? We can verify the global equilibrium. So we can sum forces in the x direction, right? That would be this x, this would be y, and then of course z is the rotation out of the plane. But in the x direction we have 15 Kips, and then that's opposed by these 2 reactions, right? And those all sum up to 0, right? Saying everything to the right is positive, right? And then vertically, right, we have this reaction and this reaction adding up to 15 Kips, which is the resultant load, or the total load, of this distributed load of 1 Kip per foot over this length of 15 feet. Okay, so that's what we have here. And then we can sum moments about the z-axis from any point. And I believe this equation is written for moments about this point over here, right? So we get the 15 kips, or excuse me, this 15 kips times 12 feet, all right? And then we get this 15 kips times its moment arm of 7.5 feet, all right? And then we have the moment reaction, all right, as well as the reaction, or excuse me, the moment produced by this reaction here, which is what that is. And this, you can verify, all sums up to 0. So global equilibrium is satisfied. Okay, so this concludes our video on the direct assembly of reactions. All right, in future analyses, we'll look at more systematic ways to do the direct assembly, but this is a good review of how to do these analyses by hand. Okay, thank you for watching.